Now we will talk about tempered distributions. This is the class of distributions to which we will extend the definition of the Fourier transform. Okay, so we saw that d of Rn was contained in S of Rn and that is contained in E of Rn. And this we know is dense, okay, S of Rn, because d of Rn is dense in E of Rn, this is also dense. D of Rn is also dense in S of Rn. Suppose you take phi in D of Rn and you take phi identically 1 on the unit ball with center at the origin, of course, and you set phi m of x equals phi of x by m. Then phi m will be identically 1 on the ball of radius m, okay, and then if you take f in S of Rn, it is easy to check that phi m of f, which is now a C infinity function with compact support, therefore it is in S of Rn, goes to f in S of Rn. Therefore this is also dense. D of Rn is densely included in S of Rn, S of Rn is densely included in E of Rn. When you have topological vector spaces with dense and continuous inclusions, then you automatically have the opposite for the duals, namely E prime of Rn can be identified with a subspace of S prime of Rn, which can be identified as a subspace of D prime of Rn. So this is the space of all distributions. This is the space of distributions with compact support, and this we call as the space of tempered distributions. Okay, so tempered definition, this subspace S prime of Rn of D prime of Rn is called the space of tempered distributions. Okay, so now let us look at examples of tempered distributions. So first example, so T in E prime of Rn, that means a distribution with compact support, implies T is in S prime of Rn, as we have just shown. Okay, so in particular the Dirac distribution is a tempered distribution. Okay, so example 2. Let mu be a measure on Rn which is slowly increasing. What does this mean? That is, there exists a positive integer k such that you have integral, so there exists a non-negative integer k, let us say, so k greater than or equal to 0, such that we have d mu of x over 1 plus mod x square to the k d mu of x, sorry, we already written that, over Rn is less than plus infinity. Okay. So in particular any finite measure, because k can be taken as 0 is slowly increasing. Lebesgue measure is slowly increasing because you know k is greater than n over 2. Okay. So now if such a measure which is slowly increasing, you define T mu of f equals integral over Rn f d mu, okay, and this is for all f in S of Rn. Okay. So then you T mu is a linear functional and mod T mu of f is less than or equal to sup mod fx into 1 plus mod x square to the power of k over all x in Rn into integral Rn d mu x by 1 plus mod x square to the k, and therefore this is finite, and also it shows that if fn goes to 0, so this is finite, and if fn goes to 0 in S of Rn, this will go to 0. This implies that T mu of fn goes to 0. So this implies that T mu belongs to S prime of Rn. So any measure which produces this. Okay. Then 3, this is very important. So example 3, 1 less than equal to p less than equal to infinity, then Lp of Rn is in S prime of Rn. In fact, it is a continuous inclusion also. So if you take f, let us first take, so if you have f in Lp of Rn, so it's a locally integrable function as a distribution. So if phi is in S of Rn, the definition is of course Tf of phi, which extends the definition of a distribution, is integral f phi dx over Rn. Okay. So let us assume that 1 is less than p less than infinity and 1 by p plus 1 by p prime equal to 1. So you have the conjugate exponent. So if you have k greater than n over 2p dash, this implies that 1 plus mod x square gx equal to 1 plus mod x square to the minus k will belong to np dash of Rn. So by Hölder's inequality, you have Tf mod Tf of phi is less than or equal to sup 1 plus mod x square to the k mod fx x in Rn of norm f, so that comes out, and then I multiplied and divided by 1 plus mod x square power k, so one of them came away here, so you get norm f sorry, here it should be phi because phi is the argument. Okay, so norm f in Lp and into norm g in Lp dash. Okay, so this shows that this is finite, and if phi n goes to 0, you have phi n goes to 0 in S of Rn. This implies that Tf, so this is finite, Tf of phi n goes to 0 in Tf phi n goes to 0. Okay. So this also shows that f and if fn goes to f in Lp, you will get that Tfn phi goes to Tf of phi for every phi in S of Rn. and this is the sequential continuity which we will use for the linear maps, as we already said, and on the Schwartz space, and therefore you have that f going to Tf is continuous from Lp of Rn into S dash of R. Okay, so you have that all LP functions are in fact in S prime of Rn. Now if P equals 1, then you have mod Tf of phi is less than or equal to norm phi L infinity and then norm f L1. So there is nothing to do, so it's automatically, it shows the continuity, and if P equals infinity, you have now mod Tf of phi is less than or equal to sup of 1 plus mod x square to the k mod phi x x in Rn into norm f L infinity and integral norm g in L1 where k is now greater than just n by 2. Okay, and this again tells you that this is in S prime. So this completely establishes our claim that LP for all 1 less than or equal to P less than or equal to infinity is in fact embedded in S dash of Rn continuously. So now we are going to define definition. Let T belong to S prime of Rn. Okay, then the Fourier transform of T denoted T hat is defined by T hat of f equals T of f hat for every f in S of Rn. So if f is in S of Rn, f hat is in S of Rn and T is in S dash, and therefore this makes sense. So this definitely makes sense, and we know that f going to f hat is a continuous from S to S, and therefore if fn goes to 0 in S, f hat n will also go to 0, and therefore Tf hat n will go to 0. So this implies that T hat belongs to S dash of Rn. So it is a tempered distribution automatically. So this is a definition. So this is what we could not do because of the Paley-Wiener theorem for all distributions, because you had, when we want to make this definition, phi hat refused to be inside the space of continuous functions, C infinity functions with compact support, whereas the Schwartz space is like that, and therefore we can use this definition. So now you have that S of Rn is contained in L1 of Rn and that is contained in S dash of Rn. So we seem to have two definitions of the Fourier transform. One is the Fourier definition because S of Rn is subset of L1, and therefore you have that S of Rn gets a definition of Fourier transform from L1. But S of Rn is also contained in S dash of Rn, and therefore S dash of Rn gives you by the above definition another. So we want to know that these two are not different. So let F belong to S of Rn and let G also belong to S of Rn. So Tf hat of G will be Tf of G hat, that's equal to integral over Rn Fg hat. But we have proved the weak Parseval relation for functions in S of Rn. This is equal to integral over Rn f hat G dx, and f hat is also in S, and therefore this is nothing but T f hat acting on G. So Tf hat is nothing but T of f hat, namely if f is a function in S of Rn considered as a tempered distribution, then the Fourier transform of it is nothing but the Fourier transform generated by the usual Fourier transform from L1. Therefore, there is no ambiguity, both definitions coincide, and therefore that is fine. So, now let us prove the following theorem, which generalizes the properties of Fourier transform of functions. So, let T belong to S dash of Rn and let alpha be a multi-index. Then d alpha of t hat equals minus 2 pi I to the mod alpha x alpha t hat. So, x alpha t is again a tempered distribution, because if you have x alpha t acting on any f, this is equal to t of x alpha f. This is the distribution definition for multiplication by C infinity function, but multiplication by monomials will still keep f into itself. So, this makes sense, and of course, you have the convergence properties. Therefore, this defines a tempered distribution. So, x alpha t is again a tempered distribution, and therefore d alpha t. So, exactly like when you want to differentiate, you multiply the distribution by a polynomial and then take the Fourier transform and put an appropriate multiple of minus 2 pi I, and dually you will have d alpha t hat is equal to 2 pi I mod alpha times xi alpha acting on t hat. T hat is now a tempered distribution. You can always multiply by means of monomial. Okay, so let us prove this. So, let f belong to S of Rn. So, what is x alpha t hat f? Is equal to x alpha t acting on f hat, and that is equal to t of x alpha f hat. But that is equal to, we have seen this, x alpha f hat is 1 by 2 pi I to the mod alpha t of d alpha f hat, and that is equal to 1 by 2 pi I to the mod alpha of t hat d alpha f. And that is equal to 1 by minus 2 pi I to the mod alpha of d alpha t hat acting on f, and therefore, from this you cross multiply, you get your answer. Other statement follows similarly. Exercise. Okay, so you can just check it, it's a trivial thing. So, you now theorem again. So, we know that the Dirac distribution is very special, and so let delta denote the Dirac distribution concentrated at the origin. On R. Okay, then you have delta hat equal to 1. 1 is a constant function. Constant function is slowly increasing. Okay, so we integral c, we know that that's a slowly increasing function. So therefore, this is again in tempered distribution. So delta hat equal to 1. Now d delta by dxk hat equals 2 pi I xi k. This is again a polynomial, so it is fine. So then 1 hat is equal to delta. So delta hat equals 1 and 1 hat equal to delta. So proof, let phi belong to S of Rn. So delta hat phi is delta of phi hat, which is phi hat of 0, which is integral over Rn phi hat of 0 e power minus 2 pi I x 0, x dot 0, that will be just 1 into phi of x dx, and that is equal to 1 t of 1 acting on phi. So constant function acting on phi, and therefore this is delta hat equal to 1. Okay, now d delta by dxk hat by the previous, whatever we proved previously, is 2 pi I psi k delta hat, and that is equal to 2 pi I psi k. Okay, finally you have 1 hat of phi, that is equal to integral over Rn of phi hat x dx, but integral of phi hat x dx is nothing but phi of 0 by the Fourier inversion formula, and then that is equal to delta phi. Okay, and therefore we have all these very nice results. So finally we conclude this section with one more question of consistency. So you have S of Rn, we already saw had two definitions, one from S dash and one from L1, and we saw that those two definitions of the Fourier transform were consistent. Okay, now you have S of Rn is contained in L2 of Rn, which is contained in S dash of Rn. So on L2 you have two definitions of the Fourier transform, one considering it as S dash, the other is got by density, namely the isometry P, which we defined last time using the Fourier inversion formula, and therefore we want to know if these two are the same. So you have let F belong to L2 of Rn. So Fn in S of Rn, Fn converges to F in L2 of Rn because it is dense, we know that. Okay, and then what do you have? L2 to S dash is continuous, and therefore you have Fn converges to F in S dash of Rn. And this implies, so what does, so if Fn converges to F in F dash, that means Fn of phi, Fn integral Fn phi will go to integral F phi for all phi in S. So this is S dash in S of Rn. But this also implies that Fn hat goes to F hat, because Fourier inversion formula. So you can think of Fn phi hat goes to F of phi hat for all phi in S of Rn, because and this implies that integral Fn hat phi by the goes to integral F hat phi. Okay, so this tells you that in S dash of Rn. On the other hand, you have P of Fn being an isometry will go to P of F in L2 of Rn, and that implies that P of Fn goes to P of F in S dash of Rn in the same way. We just saw that. But P of Fn is what? P of Fn equal to F hat n, because this is the Fourier transform of P. Fn is in S dash, S remember, and therefore you have that P of Fn is same as Fn dash goes to P of F in S dash of Rn. So this implies P of F, the limit is unique, and therefore P of F equals F hat. So that settles it. Okay, so we will stop here. We will now do some more exercises before coming to an end in this chapter.